Okay, so last time we took a look at the policy gradient algorithm. Pop up on the screen in a second, hopefully. So for starters, I'd like you to take a couple of minutes to turn to the person next to you and see if you can explain each of these parts of the policy gradient objective. And I would recommend starting at the bottom, because the bottom RT is part of it, of A hat, which is part of policy gradient loss. Okay, who was able to explain RT? Show of hands. How about A hat T, and then all the way up to the policy gradient loss? All right, let's start at the bottom as a review. Okay, so RT, if you remember, that we are going to be doing online learning, and so RT will be the actual experience reward from an entire rollout where we chose actions at each step. And it will be a sum of discounted rewards, where the first reward at time step t plus 1 is undiscounted. The next reward has a discount of gamma. The next reward has a discount of gamma squared, etc. Okay. Yeah, question. Yeah, gamma is between 0 and 1. Yeah, question. Yeah, a rollout is a run through the environment. So it could be a complete run. It could also be a partial run. So one that reaches a terminal state, or one where you just have a window of 20 time steps. Yeah, Tim. Correct, yes. So RT can only be calculated, once we've experienced that rollout in the environment. And it's actually calculated going backwards. So we start with, start by calculating R sub capital T, which is the last time step of our environment. Then we use that to calculate R sub capital T minus 1, and so on. And so we have rewards associated with each time step. Discounted sums of rewards associated with each time step. Yeah. These are the actual rewards. Yep. Yep. Okay. So then from RT, we are going to calculate our advantage. Our advantage will be the difference between our experienced reward and the estimated value of that current state. So the value function, which, if you remember, is going to be a parameterized neural network, its job will be to predict the discounted sum of rewards for that state. Question. So do we want V of ST to estimate the sum of rewards for taking a random action out of state ST, or from taking the maximum value action, or something else? What do you think? I heard maximum. That is correct. So we want V of ST to match the value out of state T given our policy. And we want our policy to be taking the maximum value action. Good. So this advantage will tell us how our reward compared to our prediction of our reward from our value function v. Any questions on that? Yeah. Good question. So the question is whether, so for this policy, we take the maximum. Would we ever do this for a policy where we don't take the maximum? So I don't know. The short answer is I don't think this would work as well if that was the case, because yeah, then the value function would be trying to estimate the value of the state given some non-optimal policy, which just doesn't really feel right, you know? Yeah, follow-up question? Yeah, so if you were, well, I mean, if you wanted to get fourth place, then that would probably be like your maximum value. So you could still do on policy learning. You would just have different rewards for different things. You'd have a higher reward for being in fourth place. So you could still use this for different objectives. Yeah, Brendan.
So the function really have a lower value the greater it is.
Correct. Well, I mean, so keep in mind that these rewards can also be negative. So yeah, but assuming that you're accumulating rewards, like positive rewards throughout the environment, then yeah, V will be a smaller number as you get closer to the end. Yeah, question. Yes, good question. So the question is whether the value function is looking at the same horizon as the R sub t, and the answer is yes, because we're training V to match R sub t. So yeah. Another question. So the question is, if V is trained well, wouldn't A sub t always be 0? The answer is yes. Exactly, yeah. So once the value network is learned, we no longer have any advantage function. And so the value network stops changing. Yep. All right, so then we have our advantage function. And then we are going to compare that to what our policy says should be the action that we take. And so if our advantage function is positive, then the gradient will cause our policy to increase the likelihood of that action. If the advantage is negative, then it will decrease the log probability of that action under our policy. Any questions on the policy gradient algorithm? Yeah, Tim. Correct? Yeah, so you're asking a good question, which is so is pi sub theta a vector? Is the advantage a vector? I actually was reviewing this and didn't have time to completely check this. I believe actually that because R sub t corresponds to taking a specific action, that that as a result, A sub t also corresponds to taking a specific action, and therefore we only take the probability of one action. And so each of these would be scalars, not vectors. I believe that's the case. I'm going to go back and double check whether these are scalars or vectors after this class, and I will post about it on the Slack. But I'm pretty sure that yeah, your policy of the given action is a scalar as well as the advantage of that action. Yeah, question. Yes. So basically, yeah, what you said is true. Basically, yeah, you made the good point of working this out. So probability will be between 0 and 1. So log of that will be negative. So, and we're trying to minimize that negative. Yeah, the product of that negative number with the advantage, and yeah, if we take the gradient and the advantage is negative, then the log probability, we want to decrease the log probability, which means, or wait, no, yeah, increase, yeah. If advantage is negative, then we want to decrease the log probability. And yeah, so you can try to chase those negative signs and work it through to make sure that you're convinced of that objective function. But yeah, yes, that is correct. Okay. So we're going to introduce a modification to this objective based on the idea that occasionally, if we have a very large advantage, we can end up with with certain actions becoming so probable that it basically takes us to a part of our action space that's very hard to get out of. And so as a result, we're going to introduce this trust region policy optimization objective, which maximizes, instead of this log probability, it's going to maximize the ratio between a new policy and an old policy. And in fact, these can be shown to be equivalent objectives. But then we are also going to introduce this constraint on our on how much our updated policy can diverge from our current policy. And so basically the idea behind that is that we're going to define a region denoted by this hyperparameter delta that where we are not allowed to update our policy outside that region. And so, however, it turns so this was a paper, the Trust Region Policy TRPO paper, but it turns out that it's pretty difficult to compute this KL divergence. And so, as a result, we are going to do something that is equivalent but much simpler. And this is that objective. We are going to take this ratio, R sub t of theta, the ratio between the new policy and the old policy, and we are going to clip that ratio between two values given by a hyperparameter epsilon. And this has the same effect as enforcing that KL divergence constraint on the ratio of those of our policies, but it's computationally much faster and simpler to implement. And so, yeah, let's go through this loss clip objective turn by turn. So starting with this E on the outside. Anyone have an idea what this E on the outside refers to? Yeah, Jacob? Expectation over T. So we're going to say over all time steps of of, then we're going to take the minimum of our ratio multiplied by our advantage and the clipped ratio and our advantage. So what this clip operation does is it says if R is between 1 minus epsilon and 1 plus epsilon, then we leave it as it is. But if it gets above 1 plus epsilon or below 1 minus epsilon, we set it equal to be 1 minus epsilon or 1 plus epsilon. Does that make sense? So basically, it's a function that bounds how large that ratio can be. And this is a visualization of the effect of this clip operation. So on the y-axis is our clipped loss, and on the x-axis is our probability ratio. And so if our advantage is positive, then our ratio is limited to be no larger than 1 plus epsilon. And if our advantage is negative, then our clip loss can be no smaller than 1 minus epsilon. And this enforces our updates basically being small enough that they don't change our policy too much in a single time step. All right, any questions on this clipped objective? Yeah, Brendan. So you're talking about here. So yeah, so for positive advantage, I'm not sure why it's showing the everything below 1 here, because really what is relevant is when the ratio is positive. And likewise for this other side. So you don't need to worry about the unbounded below or unbounded above side. Okay, so our full objective is going to be, and this will be our objective function for the PPO algorithm, is the expectation over time steps of our clip loss plus our, any idea what this second term is? LVF. This is going to be our value function loss, which remember is our value network learning to predict R sub t. And then this S of pi, which is a regularization term. So we want to minimize our value function loss while so we want our value function loss to be as, actually I'm not sure if this is negated or not. But yeah, basically we want to minimize the difference between our value function, our predicted reward, and the experienced reward, and then maximize the log probability of an action times the advantage of that action. Okay, so additionally, we have 2 networks that we're training, but both of these networks are going to operate on our states. So we're going to have a value network that takes as input a state, and let's see, which one is value? The left side is the value network. So the value network will take as input a state and predict a value of that state. The policy network will take as input a state and predict actions out of that state. And you can imagine that a lot of each of those networks will be just extracting features from the image. And so we're going to share parameters between our policy and value networks up to a certain point, and then we will have what's called like a policy prediction head on the policy network, and then a value prediction head on the value network. Any questions on that idea of sharing parameters, basically sharing our feature extractor? Yeah. The policy network does have access to the state. So that's the state is this observation, the blue box at the top. Okay, can you ask your whole question again? Sorry. Yeah, so the question is, it seems like knowing the output of the V head would be really helpful for knowing your policy. So remember that the value head says nothing about actions. It just says things about states. So the value network only has one output, whereas the policy network has a distribution over actions. And so the value network doesn't necessarily tell you anything about the relative value of each action. Does that make sense? Okay. And yeah, this is a specific case of a more general algorithm called the advantage actor critic algorithm. And so our policy network, we're going to call our actor, and the value network, we will call the critic. And I mean, you bring up a good point that in a way, the value network is informing the policy network, because the value, the policy network is trying to maximize our advantage compared to what the value network is giving us. Okay, so this is the PPO algorithm, the proximal policy optimization algorithm. So we are going to, for m iterations and for n different actors. So another thing about this algorithm is that it's parallelized. And so we're going to be running a slightly modified version of it. So they have n actors, and for each of those actors, they run a policy in an environment for t time steps, compute advantage estimates from those discounted sums of rewards, and then optimize our our objective L with respect to t, and repeat. So we are going to have a slightly modified version. We are going to drop the entropy term of the PPO objective, and we will only have the clip loss and the value function loss. So our algorithm will be initialize our policy network and our value network for a certain number of epochs. We compute a set of trajectories by running our policy in the environment. We compute our discounted sums of returns, compute our advantage estimates based on those returns and our current value function, and then maximizing the PPO clip objective. So we'll optimize the clip objective, and then we will optimize the value function objective. And so this is just a diagram of how OpenAI implemented this algorithm using parallelization with their agents in the different environments. Yeah, and then this is a diagram of they did a hyperparameter sweep over the different hyperparameters of this algorithm and found that an epsilon of 0.2 was the best trade-off for for our how much we allow our policy to explore. And yeah, so these are the results of the PPO algorithm on several different games. So this is half cheetah, where you're trying to teach a simulated cheetah in a physics simulator to run. Similar thing for teaching this little hopping agent that kind of looks like the Pixar lamp, trying to teach it to hop. So yeah, you can see that compared to other actor-critic algorithms, PPO seems a lot more stable, allowing it to learn a lot faster. Any thoughts or questions on PPO so far? Yeah, Brandon. Yeah, so DQN and PPO are both deep reinforcement learning algorithms. And that's going to be it for reinforcement learning. Any questions on the lab and how we would actually implement either of these algorithms for the lab that is due this Saturday? Okay, well, yeah, I will have office hours today after class, as well as the TAs have quite a few office hours in the next couple of days. So definitely see them if you run into trouble, but yeah, good luck on the lab. Also a reminder, your data sets for your final project are also due this Saturday. So the specs are on Learning Suite, but basically we're looking for some sort of visualization of your data, and it's showing that you have basically a way to interface with that data set for your neural network. Any questions on the data set assignment? Yeah. So we're asking you to turn in an IPython notebook with basically some sort of code that interfaces to your data set and visualizes some aspect of it. Yeah, just like showing the image or printing out in a list or something like that. Yep. It doesn't have to be something super complicated. We're just trying to help you have kind of an intermediate checkpoint to help build some momentum on your final projects. Yeah. Yeah. Mm-hmm. Yeah. All right. Okay, so now the moment you've all been waiting for, we are actually getting to GANs. I know I've said this like 6 times, but we are actually doing it today. So just for starters, see if you can turn to your partner and explain the difference between log likelihood and sampling for generative models. This was from about a week and a half ago. So hey, does someone want to take a shot at explaining sampling? Yeah, Joseph? Great. Yeah. So yeah, that's exactly right. So to reiterate what Joseph said, log likelihood and sampling are kind of opposite. So for log likelihood, we are given a sample X. So let's say we're talking about the distribution of images. We're going to take an image X and calculate the probability density function of that image under a given model. So that's going to be some number that represents the probability weight of how likely that image is relative to other images. So you can think that, like, for log likelihood, an image that's just gray noise is going to have a much lower log likelihood than something that's like an image of a person or a cat or any image that was actually taken from a camera. Okay, so then sampling, on the other hand, we don't have an image. We want to generate an image. We want to generate an image from a probability distribution over images weighted by the probability of that image. So we want to be able to generate images of cats, for example, and we want realistic images of cats to be, we want to sample realistic images of cats more often than we sample images of horses or just white noise. Any questions on log likelihood versus sampling? Okay, so again, so previous approaches to these generative models, we're able to do log likelihood. We're able to calculate log likelihood by using maximum likelihood objectives, but it was really hard to, it becomes pretty hard to sample images from these very high dimensional probability distributions. So the whole idea for GANs is that we want to sample directly without even knowing our probability density function, without knowing the log likelihood. And this is the setup. So we are going to set up a 2-player zero-sum game between a generator and what we will call a discriminator. And so we're going to basically train 2 neural networks to compete with each other. So a zero-sum game is basically, it comes from game theory, and it is a map of decisions for you and your opponent, where you and your opponent's winnings sum to 0. And the minimax theorem says that a rational mixed strategy exists for all such games. So based on that, we're going to set up this discriminator D and generator D. So D's job is to discriminate or classify between a sample from the data distribution and a sample from the generator G. So we're going to take a sample from our generating neural network, and then take a sample from our actual data set and ask the discriminator to tell us which one is a real sample and which one is not. G, on the other hand, is going to try to trick the discriminator by generating samples that are hard for D to distinguish from samples from the data distribution. And so this is how it looks. And actually, before I let you see that, any idea how you might try to set up a generator neural network? Like, for example, what would you choose as your inputs and your outputs for such a network? So to be honest, the right answer is not super intuitive and probably not something I would have thought to do. But yeah, Joseph, what do you think? Oh, that's an idea. So the idea is to take as input a likelihood and generate an image according to that likelihood. That's a really interesting idea. So yeah, that's a really interesting idea. Yeah, any other thoughts, Dane? There you go. That's another interesting idea. So rather than taking the likelihood as input, take a label as input and generate an image. I really like that idea, and basically reverse CNN architecture or something like that. Cool. Yeah, Brandon. Take as input a real image and output a drawing of it. Interesting. So yeah, the tough thing about the generator is that we want the generator to learn to discriminate, to generate images kind of from scratch. And so we don't really want to give the generator as input something that's realistic. It's an interesting thought. But yeah, in this basic GAN setup, we're not going to take as an image as input. I know where you're going off of because of your final project, which I know has to do with GAN. So there are going to be some generators that do take images as input, but not in our basic GAN scenario. Okay, and did I see some other ideas? Yeah, Michael. Take a random image. Oh, that's an interesting thought. So take a random image and trying to produce a real image. Yeah, I'm really liking these ideas, guys. Honestly, like this. I like the fact that your minds are untainted with how GANs actually work, because I think a lot of these ideas would be really interesting to try and see how they compare to what they actually do. Did I see one other? Okay. So this is how they actually do it. So kind of similar to Michael's idea, where you take start with a random image. We're going to start with a randomly sampled vector. It's also kind of similar to Joseph's idea, where we are going to take as input a probability. Instead, we're going to sample a vector that has some probability under a Gaussian distribution. And so that will be the input to our generator, which will be a neural network that, kind of like Dane says, works like a reverse CNN, and or you could think of it as like the second half of a UNet that takes a vector and converts it into an image. And it does that by using transpose convolutions, just like you used in your UNet. And then, so then we will take that generated image, X over here, and a true image, we should have called that X prime or something. And we are going to feed both of these images into the same discriminator, and then try to get, so the job of the discriminator is to classify the true image as true and the generated image as false. And the job of the generator is to generate images that are classified as true images. Yeah, question. Good question. Do you need to use a pre-trained discriminator? No. So the discriminator is initialized randomly. And so it basically learns from scratch to distinguish real images from fake images. Yeah, Jared. So yeah, practically you feed them one at a time, and you try to maximize the likelihood of the true images while minimizing the likelihood of the fake images. Yeah, so it's not like it only ever takes one image. The discriminator only ever takes one image as input. Okay. Yeah. Yeah, so good question. So the question is whether whether the generated image needs to look like the real image. And the answer is no, because again, we're feeding these in separately. And so we're not trying to match to say whether they match. Yeah. Exactly. So yeah, we just need a random data set of images, and then our generator will learn to produce images that look like they came from that data set. Yeah, Travis. A good question. So the question is, why do they choose to sample Z from a Gaussian distribution? One reason, I think, is because you can know we know the probability density function for a Gaussian distribution. So we can take a Z vector and get out a log probability. And so we can know the log probability of any sampled image from our generator. And the Gaussian distribution also, you could also do like a uniform distribution, but then you wouldn't have regions of higher and lower density like you do with a Gaussian as well. So I think Gaussian is a pretty good choice for that reason. Yeah. Totally. Yeah. So so what you described is exactly the job of the discriminator, is to look for artifacts of machine generation and pick up on those to basically distinguish those generated images from real images. And so then the generator then in turn has to try to not produce artifacts that make it look like it was generated by a machine. Yep, great. Great point. Yes, that is a very common problem with GANs. So Drake pointed out, like, what if one of these networks gets so much better than the other that the other just can't even do anything to fool it and is not able to learn at all? And that is a real problem. And so often what we see is the discriminator gets really good and makes it hard for the generator to continue learning. So that is definitely a difficulty with training GANs. Yeah, Spencer. Totally. Yeah, you could definitely imagine training schemes where if you see the discriminator start to get too good, you weight the generator loss more. And if you see the generator start to get too good, you weight the discriminator loss more. Yeah, so you could totally imagine things like that. And I'm pretty sure that things of those sort have been done. One more question on this. Can you, with this setup, determine the log likelihood of a real image? Can you do exact log likelihood calculation? The answer is no. So there's nothing here that allows us to plug in a real image and get out a probability. We can figure out the probability of generated images by taking the Z vector that generated that image and calculating the probability density function of that Z vector, but we cannot calculate the actual probability of real images. So GANs are great for sampling, but not great for calculating log likelihood.